angle of a cyclic quadrilateral is equal to the interior opposite angle, and then you get your 2 marks for writing such. Okay, so let me teach you how you can answer 7.2. It's very much important because these questions it's always give people hard time whenever they are trying to answer them, right? So let me teach you how you can answer this. In the diagram, M is the center of the circle and the diameter AB is produced to C. Always when you read the first sentence, make sure that you look for whatever that they were talking about. Okay, so they said M is the center, right, as you can see here, and the diameter, whenever they talk about the diameter, you know, diameter subtend a 90-degree angle. So it's basically angle in a semicircle. Okay, so the angle in semicircle, it's as D2 and D3. These two angles they form a 90 degrees angle, complementary angles. Yes. And then now let's move. ME is drawn perpendicular to AC such that CDE is a tangent to the circle at D. Okay, so they're talking about ME. This is ME, and then the ME we're saying it's perpendicular to AC, right? Okay, we can see that, and then from there they're saying CDE is a tangent at the circle at D. Okay, I can see that. So ME and chord AD intersect at F. This is the point of intersection. So now they're saying if D4 it is equals to X. Let me see. Oh, D4 is this one here. Is this angle here? Let me show you the angle that they're talking about. Is this angle here? D4. This angle. They're talking about this angle. It's basically angle BDC. Yes. So it's equals to X. Write down with reasons 2 other angles each equals to X. So let's see. From the tan-chord theorem, you know that whenever you are given a line which is a tangent to a circle, it means that you need to think about radius perpendicular to the tangent, or you need to think about the tan-chord theorem. So in this case, you have this triangle here. It's basically triangle. Let me draw something here so that you guys can see what I'm talking about. So this is yes. So this is triangle ABD, okay, and BDC. So to answer 7.2.1, you are going to say, let me just write 7.2.1. Angle D4, it is equals to angle A, our angle A, which is equals to X. Why do I say D4 is equals to angle A, which is equals to angle X? It is because of tan-chord theorem. So you can just write tan-chord theorem, TCT. All right. Let's check the other angle, which is equals to X. So we know that this is your X here, this angle here. So let's try to check another angle which is equals to this X. Okay, now you can see that MA MA it is equals to MD. MA it is equals to MD. Why do you say MA is equals to MD? It is because of radii. Radii or radii. Okay. So since we know that MA is equals to MD, it means that triangle AMD, it's an isosceles triangle, okay? So since this triangle AMD is an isosceles triangle, it means that our angle A, it is equals to D2. So D2, it is equals to angle A, which is equals to angle X. Oh, sorry, angle A, D2 is equals to angle A, which is equals to X, sorry for that, okay? And the reason for this, it will be angles opposite equal sides. So that's the reason. All right, let's move. Okay, all right, it means 7.2.1, we are done with it. And then you get your 4 marks for writing that, okay? Let's move to 7.2.2. Prove that CM is a tangent at M to the circle passing through M, E, and D. So basically now we need to prove that now this line CM is a tangent, okay? We need to prove that it's a tangent. So basically we need to make sure that you prove that M1, this M1, our M1 here, must be equals to angle E. Our angle E, it can be angle MED. You know what I'm talking about. So now you can say that you can prove using this triangle MED, or you can use the triangle MEC, or you can say MDC. You first determine angle C, and then from angle C you can be able to determine angle E, because we know the whole angle of EMC, but nevertheless it's fine. Let's check something here. You are told that MD is perpendicular to EC, right? So now we know that M1 plus M2, let me just write 7.2.2. M1 plus M2, it is equals to 90 degrees. This is what I'm talking about, yeah? The 90 degrees that I'm talking about. This is 90 degrees, okay? So since it's 90 degrees, why do you say this is 90 degrees? It is because we have ME, which is perpendicular to AB. So the reason will be ME is perpendicular to AB. All right. And then from this part here, you can say that M1, our M1, because we are looking for this angle M1 so that we can prove that it is equal to angle E, okay? So M1, it is equal to 90 minus M2, right? Okay. So now we have to find this angle E. Well, now we know that M1 is equal to this. Okay, so it means that angle M2 here, angle M2, it can be equal to 90 minus angle M1. So now we can say that D1 plus D2, it is equal to 90 degrees as well. Why do you say this? It is because of the radius perpendicular to the tangent. Okay. And then from this part now you can say, oh, now I have to determine angle E. So our angle E plus angle M2 plus angle D1 plus D2 is equals to 90 degrees. Why do you say it was equals to 180? Sorry for that. Why do you say this? These are sum of angles in a triangle. Ne? So it's sum of angles in a what? In a triangle. Sum of angles in a triangle. And then from this part here, angle E, let's check angle E. Our angle E, it is equals to 180 minus, because M2 it's 90 minus 1, right? So you can just write it's minus 90 plus M1. Okay, minus 90 plus M1. And then this D1 plus D2, we know that it is equals to 90 degrees. We spoke about this, right? So you're going to say it's minus 90. This minus 90 is for D1 plus D2. Therefore, from this part, 180 minus 90, it is equals to M1. So angle E, it is equals to M1. All right, thank you very much. And then let's move to 7.2.3. 7.2.3. Prove that FMBD is a cyclic quadrilateral. FMBD is a cyclic quadrilateral. So actually we need to prove that we do have a small circle passing through these 4 points here. Okay, so basically when we prove when we prove that FMBD is a cyclic quad, so the reason at the end it will be the converse. It's a converse because the circle, it is not drawn for you. You have to prove that there is a circle there. So let's see what we can do now. Since we're talking about all these 4 points, FMBD, it means that we are going to prove using opposite angles of a cyclic quadrilateral. We know that opposite angles of a cyclic quadrilateral, they add up to 108. So you can use angle F2 plus B2, or you can use angle M1 plus M2 and angle D2 plus D3. So let's check. So in 7.2.2, we proved that M1 plus M2 is equals to 90 degrees, right? So we need to check. Let's check D2 plus D3. D2 plus D3. So now you can say our D2, angle D2 plus D3. This is the angle that I'm thinking about. Let me show you this angle. Yeah, this angle, it's 90 degrees, right? So it is equals to 90 degrees. Why do you say it's equals to 90 degrees? It is because we have this diameter AB. So you know that diameter subtend 90 degrees, right? So the reason here, it will be angle in a semicircle. Wow. So since D2 plus D3 is equals to 90 degrees, we proved that M1 plus M2 is equals to 90 degrees. So M1 plus M2 it is equals to 90 degrees. Proven, right? Let me just write a proven. Therefore, we have opposite angles which are supplementary, because 90 plus 90, it is equals to 108. Therefore, you can say, therefore, FMBD, it's a cyclic quad. Why? Reason, it will be converse opposite angles of a cyclic what? Quad. Yes. You can just write that. Converse opposite angles of a cyclic quad. So FMBD, so what is a cyclic quadrilateral? Reason it will be